Have you ever stared up at the night sky and felt that overwhelming sense of wonder, the kind that makes you stop in your tracks and wonder, how did all of this come to be? Every star, every galaxy, even the very fabric of space and time itself, how did it all begin? This isn't just a question for scientists or philosophers. It's something deeply human, something we've all wondered at some point, lying beneath those infinite, glittering lights. And here's the thing, the answers we've uncovered so far are more astonishing than anything we could have imagined. Think about this for a second. Everything around you, the device you're watching this on, the air you breathe, even the atoms in your body, all of it traces back to a single, unimaginable moment. A spark in the darkness nearly 14 billion years ago that set the entire universe into motion. But how? What forces shaped the cosmos into what we see today? What mysteries are still hidden in the vast stretches of space waiting to be uncovered? That's exactly what we're diving into today, 30 of the most mind-bending questions about the formation of the universe, the kind that make you rethink everything you thought you knew. This isn't just a list of facts, it's a journey, one that takes us from the very first microseconds after the Big Bang to the sprawling galaxies we observe today. We'll explore how empty space could birth something as colossal as a supercluster, why the universe looks the way it does, and whether we're alone in this grand cosmic story. Some of these questions have answers that will leave you in awe. Others, well, they might keep you up at night. So if you're ready to go beyond the ordinary, to step into the unknown and uncover the secrets of existence itself, then let's begin. The universe has been waiting to tell its story, and trust me, you won't want to miss a single word. What if the universe began not with a whisper but a roar? The Big Bang is often described as the moment everything started, but here's the twist. We still don't know what sparked it. Imagine lighting a match in total darkness, only to realize no one knows where the match came from. That's the puzzle scientists face when they try to explain what triggered the birth of space and time. One leading theory suggests it all began with quantum fluctuations, tiny, unpredictable shifts in energy at the smallest scales of existence. In the void of nothingness, these microscopic ripples could have tipped the balance, creating a runaway expansion we now call the Big Bang. Picture a calm lake suddenly erupting with waves from a single, invisible pebble. But here's where it gets even stranger. Some researchers propose our universe might just be one bubble in an endless cosmic foam, where collisions between other universes could have set off our own. It's like two soap bubbles merging in midair, releasing enough energy to birth an entire reality. Then there's the idea of a cyclical universe, where the Big Bang wasn't a one-time event but part of an endless loop, expansion, collapse and rebirth, over and over like a cosmic heartbeat. Ancient Hindu texts spoke of universes breathing in and out, and modern physics isn't entirely dismissing the notion. Yet for all these theories, the truth remains elusive. The closer we look, the more we realize the Big Bang might not even be the true beginning, just the furthest point we can trace back. Why does this mystery endure? Because the rules of physics as we know them break down at that moment of creation. Time, space, even cause and effect, they all blur into something beyond our current understanding. It's like trying to describe the color of a shadow using only a box of crayons. The tools we have just aren't enough, but that's what makes this question so thrilling. Every new telescope, every breakthrough in quantum mechanics brings us a little closer to unraveling the ultimate cosmic riddle, how nothingness became everything. If the Big Bang marked the beginning of everything, time, space, matter, then what could possibly have come before it? The question itself feels like a paradox, like asking what's north of the North Pole. Yet some of the most brilliant minds in physics refuse to accept that the story of our universe starts with a single, unexplainable moment. They're probing the edges of reality, searching for clues in the fog of pre-creation. Take the idea of nothingness. It's not just empty space, it's the absence of space itself, no time, no particles, no laws of physics as we know them. But here's the twist. Quantum mechanics suggests that even nothing is unstable, seething with potential. Imagine a void so restless that it spontaneously births particles, like bubbles forming in a boiling pot of water. Could our universe be one of those bubbles emerging from a deeper, invisible quantum foam? Some theories say yes, that the Big Bang was just a phase transition, a cosmic switch flicked in the dark. Then there's the wild possibility of a pre-Big Bang universe. Loop quantum gravity, for instance, proposes that time doesn't actually begin at the Big Bang but rebounds from a previous collapsing universe like a cosmic yo-yo. Picture a black hole's crushing gravity reversed. Instead of collapsing into a singularity, the universe bounces back, giving birth to a new one. Ancient myths spoke of worlds reborn from ashes, and eerily, modern math isn't entirely disagreeing. String theory takes it further, suggesting our universe might be one slice of a multiverse, a four-dimensional brain floating in higher dimensional space, occasionally colliding with others. These collisions could trigger big bangs endlessly, like dominoes falling in an infinite hall of mirrors. The catch: we're trapped in our own slice, unable to see beyond its edges. But how do we study a time before time? Physics as we know it shatters at the moment of creation. It's like trying to read the first page of a book that's been burned away. Some researchers turn to the cosmic microwave background, the faint afterglow of the Big Bang, for hidden imprints of a prior universe. Others simulate conditions in particle colliders, recreating fractions of a second after creation in hopes of glimpsing what came before. The truth is, we're grappling with the limits of human understanding. Asking what was before might be like a fish asking what's outside the water. Our very framework of reality might not even apply. Yet that's the thrill of this mystery. Every unanswered question is a doorway, and behind it could lie truths more astonishing than fiction. Maybe the answer isn't a universe at all, but something beyond our wildest imaginations. One thing's certain: the deeper we dig, the stranger reality gets. The universe didn't just expand, it exploded outward faster than the speed of light, stretching from smaller than an atom to the size of a grapefruit in less than a trillionth of a second. How is that even possible? Welcome to cosmic inflation, one of the most mind-bending ideas in all of physics. Think of it like blowing up a balloon, but instead of taking a breath, the balloon inflates itself with pure energy, doubling in size over and over again before you can blink. This wasn't just fast, it was exponential. The entire universe became a runaway train, fueled by a mysterious force we still don't fully understand. Scientists call it the inflaton field, a kind of cosmic energy that acted like anti-gravity, pushing space apart from the inside. Imagine stepping on a skateboard that keeps accelerating no matter how fast you go. Except in this case, the skateboard is reality itself. But how do we know this actually happened? The evidence is written in the oldest light we can see, the cosmic microwave background. This faint glow left over from the Big Bang is like a snapshot of the infant universe. And what it shows is astonishing: a patchwork of temperature fluctuations, so perfectly balanced that they couldn't have formed without inflation smoothing everything out. It's as if someone took a lumpy ball of dough and stretched it into a perfectly flat sheet in an instant. Yet inflation isn't without its mysteries. Why did it start? And more puzzling, why did it stop? Some theories suggest the inflaton field decayed, transforming its energy into the particles and radiation that fill the universe today. Others propose that inflation never truly ended, that pockets of space are still inflating right now, giving birth to new universes beyond our own. The debate gets even stranger when you consider alternative ideas. Could inflation have been triggered by collisions between higher dimensional objects like cosmic strings or brains? Or was it a quantum fluctuation that tipped the scales, like rolling a ball down an impossibly steep hill? The wildest part we might never know for sure. Inflation happened so early, so violently, that its fingerprints are faint, buried under billions of years of cosmic evolution. What's clear is this: without inflation, the universe as we know it wouldn't exist. Galaxies, stars, even the atoms in our bodies, all of it traces back to that fleeting moment when space itself decided to run. And that's the real magic of this theory. It doesn't just explain how the universe grew, it reshapes how we think about the very fabric of reality. Imagine holding a balloon covered in tiny dots. Now picture it inflating, but instead of slowing down, the dots rush apart faster and faster, defying gravity's pull. That's exactly what's happening to our universe right now, and the culprit is something we can't even see: dark energy. Making up nearly 70% of the cosmos, this invisible force isn't just expanding space, it's accelerating the process, pushing galaxies apart at speeds that grow more extreme with every passing moment. The strangest part, we don't know what dark energy actually is. Einstein once called his version of it the cosmological constant, his biggest blunder, only for modern astronomers to confirm it might be real after all. Think of it like a property of empty space itself, a kind of anti-gravity woven into the fabric of the universe. Every cubic centimeter of vacuum, no matter how empty, could contain this energy, relentlessly stretching space-time apart. But not all scientists agree. Some propose dark energy isn't constant at all, but a dynamic force field dubbed quintessence. Picture a cosmic wind that strengthens and weakens over time, unlike Einstein's steady push. Ancient philosophers named quintessence the fifth element, the invisible substance filling the heavens. Today's physicists wonder if this evolving energy could someday rip atoms apart in a big rip, ending the universe in a final, violent expansion. Then there's the glaring contrast with its shadowy cousin, dark matter. While dark energy drives galaxies apart, dark matter's gravity holds them together like cosmic glue. One is the universe's ultimate push, the other its pull, yet both remain invisible, detectable only through their effects on the cosmos. It's as if we're studying a ghost by the footprints it leaves in the snow. The real puzzle: dark energy didn't dominate the universe until relatively recently, cosmically speaking. For billions of years, gravity kept expansion in check. Then, around 5 billion years ago, dark energy took over, as if someone flipped a switch. Was this inevitable, or is our cosmos following some hidden script? Theories range from extra dimensions leaking energy to imperfections in the early universe's structure. What's at stake isn't just academic. Dark energy determines the universe's ultimate fate: endless expansion, a catastrophic collapse, or something even stranger. Every observation from distant supernova to the large-scale web of galaxies hints that we're missing a fundamental piece of reality, and that's the heart of this mystery. The more we learn, the clearer it becomes. The universe isn't just expanding, it's running away from us. Here's something that should make your brain itch every time matter is created in the universe. Physics says an equal amount of antimatter should appear alongside it. They're like cosmic twins born together in perfect balance. So why, when we look around, does everything we see, from stars to planets to the screen you're watching right now, consist only of matter? Where did all the antimatter go? This isn't just a minor puzzle. It's one of the biggest unsolved mysteries in physics. Let's break it down. Matter and antimatter are nearly identical, except for one key difference: their charge. Take an electron, for example. Its antimatter counterpart, the positron, has the same mass but a positive charge instead of negative when they meet. Annihilation, a burst of pure energy, leaving nothing behind. According to the laws of physics, the Big Bang should have produced equal parts matter and antimatter, which would have immediately cancelled each other out, leaving a universe filled with, well, nothing. And yet, here we are. Somehow, nature cheated. For every billion particles of antimatter, there were 1,000,000,001 particles of matter. That tiny imbalance is all that's left the reason anything exists at all. Scientists call this the matter-antimatter asymmetry problem, and the leading clue lies in something called CP violation. CP stands for charge parity, a fundamental symmetry in physics that says if you swap a particle with its antiparticle and mirror the reaction, the laws of physics should stay the same. But in the 1960s, researchers observed something strange. Certain particles decayed slightly differently than their antimatter counterparts. It was like flipping a coin and discovering it lands on heads just a fraction more often than tails. This tiny violation of symmetry might explain why matter won out, but here's the catch. The effect is far too weak to account for the overwhelming dominance of matter in the universe. That's where baryogenesis comes in, a set of theories attempting to explain how matter gained the upper hand. One idea involves ultra-rare particles that decayed more into matter than antimatter in the early universe's extreme heat. Another suggests the presence of cosmic phase transitions, like bubbles of false vacuum collapsing and releasing extra matter in their wake. Some even propose that antimatter wasn't destroyed at all, that it's hiding in distant regions of space separated from us by vast voids. The stakes couldn't be higher. If we solve this mystery, we don't just understand why we exist, we uncover new laws of physics. Experiments like the Large Hadron Collider are smashing particles together, searching for even the slightest deviations in how matter and antimatter behave. Others are hunting for ghostly neutrinos, which might hold the key to why nature prefers matter. Every time we think we're close, the universe throws us another curveball. So next time you look at your hand, remember those atoms shouldn't be here. They're the survivors of an ancient cosmic battle, a one-in-a-billion fluke that shaped everything. And somewhere out there, the answer is waiting. For 380,000 years after the Big Bang, the universe was too hot for atoms to exist, just a searing soup of free electrons and nuclei zipping around at unimaginable speeds. Then, almost suddenly, everything changed. As space expanded and cooled, electrons finally slowed down enough to be captured by protons, forming the very first atoms. But these weren't just any atoms, they were the simplest building blocks imaginable. Hydrogen, with its single proton and electron, paired with a sprinkle of helium and trace amounts of lithium. Here's why those elements came first. In the universe's first few minutes, conditions were perfect for what's called Big Bang nucleosynthesis, a brief window where protons and neutrons could fuse together despite the chaos. Imagine a crowded dance floor where particles keep bumping into each other. At 1 trillion degrees, protons' hydrogen nuclei collided fast enough to stick together, forming helium nuclei, 2 protons and 2 neutrons bound tight. The math is elegant. For every 12 hydrogen nuclei, 1 helium nucleus formed. Lithium, with just 3 protons, barely made the guest list, appearing in amounts so tiny you'd need a cosmic microscope to spot them. But here's the catch, that's where the party stopped. Heavier elements like carbon, oxygen, or iron, impossible. The universe was cooling too rapidly, and without the extreme pressures found inside stars, those atomic dances couldn't continue. It's like trying to bake a cake in an oven that keeps losing heat. You might get batter to thicken, but you'll never reach the finished dessert. This left the early universe astonishingly simple. A vast, dull sea of hydrogen and helium gas with no planets, no life, not even a single molecule of water. The stars we see today, they didn't exist yet. Every heavier element in your body, your phone, even the air you breathe, all of it had to wait for the first generation of stars to ignite, forging new atoms in their nuclear furnaces. That's the wild irony of cosmic chemistry. The very elements that make up most of our world couldn't form until the universe grew up a little. Those first atoms were just the opening act. The real magic happened when gravity pulled them together, lighting the fuse for everything that followed. For hundreds of millions of years after atoms first formed, the universe plunged into darkness, not just any darkness, but a profound stillness where no stars twinkled, no galaxies swirled. This was the cosmic dark ages, an eerie period when the universe expanded in silence, filled only with vast clouds of hydrogen and helium gas drifting through the void. Without light sources, space was colder and emptier than we can fathom. Yet beneath this quiet surface, something extraordinary was brewing, the slow, inevitable pull of gravity working its magic on those primordial gases. Picture a cloud of gas so massive it could span thousands of light years. At first, these clouds barely moved, their particles gently nudging each other in the cold. But gravity never sleeps. Over millions of years, tiny density fluctuations, leftover wrinkles from the Big Bang's quantum chaos, began to amplify. Wherever atoms clustered slightly closer together, their collective gravity grew stronger, pulling in even more gas. It's like rolling a snowball downhill. The bigger it gets, the faster it accumulates. As these pockets collapsed, they fragmented into smaller, denser clumps, each one a potential cradle for the universe's very first stars. These pioneers, known as population Roman 3 stars, weren't like the stars we see today. Born from pure hydrogen and helium, they lacked the heavier elements that help modern stars regulate their nuclear fires. That made them monsters hundreds of times more massive than our Sun, blazing at temperatures so extreme they'd appear blue-white to our eyes. Their lifetimes were brief but spectacular, burning through their fuel in just a few million years before ending in colossal supernova. That's where the real alchemy happened. The intense heat and pressure inside these stars fused atoms into heavier elements: carbon, oxygen, even iron elements that didn't exist in the early universe. When the stars exploded, they scattered these freshly forged materials across space, seeding the cosmos with the building blocks of future planets, oceans, and life itself. But here's the twist: we've never directly observed a population Roman 3 star. They burned out long ago, and their light is too faint for current telescopes to detect. Yet their fingerprints are everywhere. The oldest stars we can see, tiny, ancient survivors from just after the Dark Ages, contain traces of those first explosions. It's like finding pottery shards from a lost civilization. We piece together their story through fragments. New observatories, like the James Webb Space Telescope, are hunting for glimpses of these primordial giants by peering back to when the universe was just a few 100 million years old. If we spot one, it would be like uncovering the very first spark that lit the cosmic fire. Until then, we're left with a humbling thought. Every atom in our bodies, every molecule in the air, was once stardust forged in the hearts of these long-dead titans. In the early universe, galaxies didn't just appear, they were sculpted by an invisible hand, a cosmic architect we now call dark matter. Picture a vast, swirling ocean of gas, invisible currents pulling it into intricate patterns. Without dark matter's gravitational grip, those first stars might have scattered like dust in the wind, never coalescing into the majestic spirals and ellipticals we see today. The process began with tiny ripples in the fabric of space-time, imprints left over from the Big Bang's inflationary frenzy. Where dark matter clustered slightly denser, its gravity drew in hydrogen and helium like magnets pulling iron filings. Over millions of years, these pockets grew into halos, massive, invisible structures spanning hundreds of thousands of light years. Gas pooled at their cores, collapsing under its own weight until nuclear fires ignited, birthing the first stars. But this wasn't a one-step process. Early galaxies were messy, chaotic places, often colliding and merging in a slow-motion ballet that reshaped them over billions of years. Take the Milky Way. Our galaxy wasn't born this grand, it's a patchwork of smaller galaxies devoured over time. Astronomers have even identified its last meal, a dwarf galaxy called Gaia Enceladus, consumed roughly 10 billion years ago. These mergers weren't gentle. Stars were flung into wild orbits, gas clouds collided violently, triggering bursts of new star formation. Yet through the chaos, dark matter acted like a stabilizing scaffold, ensuring the galaxy's structure endured. But not all galaxies evolved the same way. Spirals like our own formed in quieter corners of the cosmos where gas could settle into orderly disks. Elliptical galaxies, by contrast, are often the products of violent crashes, cosmic train wrecks that erased their delicate spirals, leaving behind bloated, star-filled spheres. Some of the most massive ellipticals sit at the hearts of galaxy clusters, gorged on smaller neighbors until they grew into titans, the real mystery. Why galaxies stopped growing? Around 10 billion years ago, star formation peaked, then mysteriously declined. Some blame supermassive black holes whose fierce energy jets heated surrounding gas, preventing it from cooling into new stars. Others point to dark energy whose accelerating expansion made it harder for galaxies to pull in fresh material. What's clear is this: galaxy formation isn't a finished story. Even now, our Milky Way is digesting new victims like the Sagittarius dwarf, whose remnants streak through our skies. And with every telescope we build, we get closer to witnessing these cosmic dramas unfold in real time, watching as chaos gives birth to order, one collision at a time. Black holes aren't just cosmic vacuum cleaners. They might be something far stranger, the seeds of entire universes. At their cores lies the singularity, a point where gravity becomes infinite, space and time cease to behave normally, and the laws of physics as we know them simply break. Sound familiar? It's eerily similar to the conditions we theorize existed at the moment of the Big Bang: an infinite density, a point of no return. That's led some physicists to ask a wild question. Could black holes be cosmic nesting dolls, each containing a newborn universe inside? Take the idea of black hole cosmology proposed by theorists like Lee Smolin. Imagine a black hole's singularity not as an end but a bridge. When matter collapses beyond the event horizon, the extreme conditions might trigger a new Big Bang, birthing a universe with its own physical constants slightly tweaked from ours. In this view, our own universe could have blossomed from a singularity inside another black hole, part of an endless fractal of realities. It's like shaking a snow globe and watching an entire new world form from the chaos. But how would this even work? Inside a black hole, the fabric of space-time is twisted so violently that time and space effectively swap roles. Instead of moving toward an inevitable future, you're pulled inexorably toward the center. The singularity becomes your destiny, not a place but a moment in time. Some models suggest this singularity might not be a point, but a bounce, where collapsing matter rebounds into expansion, like a universe taking its first breath. Then there's the role black holes play in shaping the cosmos we see. Supermassive black holes lurk at the hearts of nearly every galaxy, their masses tightly correlated with the size of their galactic hosts. This isn't coincidence, it's evidence of a deep cosmic partnership. As these giants grew, their gravity may have funneled gas into swirling disks, igniting stars and sculpting galactic spirals. They're not just destroyers, they're architects shaping the universe from the shadows. The James Webb Space Telescope recently spotted ancient galaxies with fully formed black holes far earlier than expected, too early, according to conventional models. One explanation: these black holes didn't form from stars but were primordial, born in the universe's first seconds from dense fluctuations in the infant cosmos. If true, they wouldn't just be galaxy seeds, they'd be relics of creation itself, cosmic fossils holding clues to the Big Bang. Yet for all the theories, black holes guard their secrets fiercely. The event horizon is a one-way curtain, and the singularity remains hidden behind it. Some argue that trying to peek beyond is like asking what's north of the North Pole. The question might not even make sense. Others believe new physics, like loop quantum gravity, could offer ways to understand what happens when gravity wins its ultimate victory. Whether they're universe factories or gravitational prisons, black holes force us to confront the limits of our knowledge. They're the universe's way of showing us how much we still don't understand and how wild reality might truly be. Is the universe infinite, stretching forever in all directions, or is it finite, with some hidden edge we just haven't found yet? This isn't just a philosophical puzzle, it's a question that cuts to the heart of cosmology, and the answer could rewrite everything we think we know about reality. Let's start with what we can observe, the cosmic horizon. Because light has a finite speed and the universe has a finite age, we can only see so far about 46 billion light-years in every direction. Beyond that, the light from those regions hasn't had time to reach us yet. It's like standing in the middle of an endless ocean where the horizon hides everything beyond. But does that mean the universe itself stops there? Not necessarily. Just because we can't see past a certain point doesn't mean nothing exists beyond it, only that we're trapped inside our own observable bubble. Now, here's where it gets tricky. The shape of the universe plays a huge role in this question. Scientists measure this by studying the geometry of space itself, and so far, the evidence points to a flat universe, one where parallel lines stay parallel forever, and the angles of a triangle add up to exactly 180 degrees. A flat universe is consistent with infinity, but it doesn't prove it. It could also mean the universe is just really, really big, like an ant on a soccer field, assuming the field goes on forever. But flatness isn't the only possibility. Some theories suggest the universe might be curved either positively, like a sphere, or negatively, like a saddle. If it's a sphere, traveling far enough in one direction would eventually bring you back where you started, like circumnavigating the Earth. That would mean the universe is finite but unbounded, no edges, just a cosmic loop. A saddle-shaped universe, on the other hand, would be infinite, with space stretching away forever in a hyperboloid warp. Then there's the wild card topology. Even if the universe is flat, it might have a complex shape, like a torus, a giant cosmic donut where crossing one edge teleports you to the opposite side. Imagine playing an old video game where leaving the screen on the right makes you reappear on the left, just scaled up to the size of reality itself. So how do we settle this? The cosmic microwave background holds clues. Tiny fluctuations in this ancient light could reveal whether space wraps around itself, whether parallel lines eventually cross, or whether the universe truly has no end. So far, the data supports flatness, but the margin of error leaves room for surprises. The implications are staggering. An infinite universe means there's no limit to how much is out there. Countless galaxies, stars, even copies of you somewhere in the vastness. A finite one suggests a universe with boundaries, a cosmic scale we could, in theory, measure. And if the universe loops back on itself, that would mean reality is stranger than we ever imagined, a cosmic Möbius strip where endings and beginnings blur into one. For now, the question remains open, hanging in the void like a puzzle waiting to be solved. Every new observation, every deeper probe into the fabric of space brings us closer to the answer. But until then, we're left staring at the horizon, wondering what lies beyond the edge of our vision. Imagine if gravity were just a fraction stronger, planets would crush themselves under their own weight. If the nuclear forces binding atoms together were slightly weaker, stars could never ignite. The universe seems to operate on a razor's edge of precision, with fundamental constants fine-tuned to values that make life possible. This isn't just luck, it's a cosmic mystery so profound it's called the fine-tuning problem. Take the strength of gravity, for instance. It's roughly 10 to the 39th times weaker than the electromagnetic force. If that ratio shifted even slightly, stars would either burn out too quickly or never form at all, leaving the universe sterile. Even the cosmological constant, the energy density of empty space, is calibrated within 1 part in 100 million billion of its theoretical maximum. A hair's breadth in any direction and galaxies wouldn't exist. It's like balancing a pencil on its tip for billions of years, except the pencil is reality itself. So how do we explain this eerie precision? One answer lies in the anthropic principle, the idea that the universe must be hospitable to life because we're here to observe it. In other words, if the constants weren't just right, we wouldn't exist to wonder why. It's a bit like a puddle marveling at how perfectly its hole fits its shape. But while this explains why we perceive fine-tuning, it doesn't solve how these values came to be. Enter the multiverse theory, a cosmic lottery where countless universes exist, each with its own random set of physical laws. Most might be barren, collapsing instantly or lacking structure altogether. But in a few rare universes like ours, the numbers align just right for galaxies, stars, and life to emerge. Think of it like rolling a million dice at once. Eventually, one lands on all sixes. The catch: we have no way to observe these other universes, leaving the theory tantalizing but untestable. Not everyone's convinced. Some physicists argue fine-tuning points to deeper, undiscovered laws. A unifying theory where these constants aren't arbitrary but inevitable. Others propose a cyclical universe where each new Big Bang tweaks the values slightly, iterating until life-supporting conditions arise. Then there's the wild card: could the universe be engineered? While speculative, even respected scientists like Nobel laureate Frank Wilczek acknowledge the eerie elegance of physics raises questions we can't yet answer. The stakes couldn't be higher. If the multiverse is real, our existence becomes a statistical fluke in an infinite sea of failed realities. If deeper laws govern the constants, we're on the verge of uncovering physics' grandest blueprint. And if the universe is fine-tuned, whether by chance, necessity, or design, it forces us to confront the most humbling question of all: why does anything have rules at all? The answer might not just redefine our place in the cosmos, it could reveal the universe's ultimate secret. What if our universe isn't alone, just one page in an infinite cosmic library where every possible version of reality exists simultaneously? The idea of a multiverse isn't science fiction anymore. It's a serious scientific hypothesis with multiple compelling frameworks, each more mind-bending than the last. Let's start with the most widely accepted version, the inflationary multiverse. According to this theory, the same process that rapidly expanded our early universe, cosmic inflation, never actually stopped. Instead, it continues in distant regions of space, creating countless bubble universes with their own unique physics. Picture blowing soap bubbles in a breeze. Each one floats away, carrying its own self-contained world inside, completely isolated from the others. Some might have stronger gravity, others might allow time to flow backward, and a rare few could, like ours, be just right for life. String theory takes this even further with the concept of the landscape multiverse. In this view, the extra-dimension string theory predicts could settle into different configurations, each creating a universe with its own fundamental constants. Think of it like a cosmic vending machine. Every twist of the dial results in a different universe popping out, with varying laws of physics. Some combinations might lead to stable atoms, others might collapse instantly into chaos. The eerie part: this could mean there are alternate realities where gravity repels instead of attracts, or where light moves at a snail's pace. Then there's the quantum multiverse, born from the many worlds interpretation of quantum mechanics. Every time a quantum particle faces a choice like whether to spin left or right, the universe splits, creating parallel timelines where each possibility plays out. Missed a bus this morning. Somewhere out there, a version of you caught it and is living a completely different day. This isn't science fantasy. It's a legitimate attempt to explain why quantum particles behave so strangely when we observe them. But here's the million-dollar question: can we prove any of this? Some physicists argue that multiverse theories are untestable by nature. If other universes are permanently beyond our reach, how can we ever confirm they exist? Yet clever workarounds are emerging. For the inflationary multiverse, scientists hunt for bruises in the cosmic microwave background, anomalies that could be imprints from collisions with neighboring bubble universes. A quantum multiverse might leave traces in particle behavior here, subtly altering probabilities in ways we could, in theory, measure. The debate isn't just scientific, it's philosophical. If the multiverse is real, it flattens our universe's significance into a statistical fluke, but it also solves puzzles like fine-tuning. In an infinite ensemble of universes, some had to be life-friendly purely by chance. Critics argue this makes science untestable. If anything can happen somewhere, how do we falsify a theory? Supporters counter that rejecting an idea just because it's uncomfortable isn't how discovery works. After all, black holes and the Big Bang were once dismissed as absurd. So where does that leave us? The multiverse remains a frontier, part math, part mystery, part mirror, forcing us to confront how little we truly understand. Whether it's real or not, the mere possibility reshapes how we see reality, not as a single stage, but as one act in an endless cosmic play. Time doesn't just pass, it has a direction, an arrow pointing relentlessly from past to future. But why? What set this one-way flow into motion, and where did time itself even come from? The answer might lie in one of the universe's most fundamental forces, not gravity, not electromagnetism, but something far subtler, entropy. Here's how it works. Entropy is a measure of disorder, and the second law of thermodynamics states it always increases over time. Think of a deck of cards shuffled. It becomes randomized, but it never spontaneously reorganizes itself into perfect suits and sequences. That's entropy in action. Now, imagine the early universe as an unimaginably dense, ultra-orderly state, a cosmic deck stacked perfectly. The Big Bang was like throwing that deck into the air, scattering it into chaos. Time's arrow, then, might simply be the universe's journey from order to disorder, with every moment pushing it further toward maximum entropy. But this raises a deeper question. Why was the early universe so ordered to begin with? Some physicists argue it's the only way time could have a direction. Without that initial low entropy state, there'd be no arrow to point forward, just random fluctuations with no clear past or future. It's like a movie reel starting on the first frame. Everything that follows depends on that first moment being sharply defined. Yet this explanation only takes us so far. What about the nature of time itself? Quantum gravity theories like loop quantum gravity and string theory suggest time might not be fundamental at all, just an emergent property like temperature arising from the motion of particles. In these models, the deep structure of reality could be timeless, with time appearing only at larger scales, the way a smooth tabletop emerges from the grain of wood when you zoom out. Picture a flipbook. The illusion of motion only exists when you flip the pages, but at its core, it's just a stack of static images. This leads to the most mind-bending puzzle of all. What, if anything, came before time? The question might be meaningless, like asking what's north of the North Pole. In general relativity, time is woven into the fabric of space-time, and the Big Bang represents the origin of that fabric. There's no before, because there's no space-time for events to unfold in. But some theories, like the Hartle-Hawking no-boundary proposal, suggest the universe could have emerged from a timeless, four-dimensional geometry, a cosmic egg with no shell, no starting point, just a smooth transition from nothingness to existence. Then there's the radical idea of causal set theory, where time isn't continuous but made of discrete, indivisible moments, like grains of sand in an hourglass. In this view, the flow of time isn't an illusion, but the result of these grains cascading in a particular sequence. If true, the Big Bang wouldn't be the beginning of time, but the first grain in an infinite chain. The challenge is this: every theory we have breaks down at the moment of creation. Entropy gives us time's arrow, but not its origin. Quantum gravity hints at timelessness, but can't yet explain how time switches on. And the concept of before time might be as nonsensical as a shadow without light. Yet in this uncertainty lies the thrill of discovery, because solving time's mystery wouldn't just tell us how the universe began. It would reveal what reality fundamentally is. At the smallest scales of the universe, empty space isn't empty at all. It's a seething quantum foam where particles flicker in and out of existence in a frenzied dance. These fleeting fluctuations might seem insignificant, but they hold the key to one of cosmology's greatest revelations: how the universe grew from absolute uniformity into the intricate web of galaxies and voids we see today. Here's the astonishing connection. During the universe's first fraction of a second, inflation, that runaway expansion, stretched these microscopic quantum jitters to cosmic proportions. Picture a tiny ripple on a pond suddenly magnified into a tidal wave as the pond grows to the size of an ocean. What began as random, subatomic twists in the fabric of spacetime became the seeds for all cosmic structure. Gravity then took over, amplifying these density differences over billions of years. Where particles clustered slightly closer together, their combined pull attracted more matter, eventually forming galaxies. The emptier regions expanded into vast cosmic voids, the universe's equivalent of deserts. But how do we know this actually happened? The proof is etched into the cosmic microwave background, the oldest light in existence. When scientists map its temperature variations, they're looking at fossilized imprints of those primordial quantum fluctuations. The pattern matches predictions with uncanny precision, like finding a suspect's fingerprints at the scene of a cosmic crime. The real marvel is how delicate the balance had to be. If the fluctuations had been much weaker, gravity wouldn't have had enough clumpiness to work with, leaving the universe a featureless gas cloud forever. Too strong, and matter would have collapsed into monstrous black holes long before stars could form. Our universe somehow struck the perfect note, a Goldilocks zone where quantum chaos could sculpt a cosmos rich enough for galaxies, planets, and life itself. Some theories suggest these quantum seeds might have even stranger origins, collisions between higher dimensional objects in string theory, or echoes of a pre-Big Bang universe. Others propose that dark matter's mysterious influence guided how these fluctuations grew into the cosmic web. Whatever the full story, one thing's certain: the largest structures in existence owe their existence to the smallest, most fleeting phenomena imaginable. The universe's grand design began with a quantum whisper, and we're just beginning to understand its echo. Will the universe end with a slow fade into darkness, a violent collapse, or something even stranger? The answer depends on a cosmic tug-of-war between gravity and dark energy, and right now, dark energy is winning. Let's explore the four most likely endings for everything, each more dramatic than the last. First, the Big Freeze, also called heat death. In this scenario, dark energy keeps accelerating the universe's expansion until galaxies are so far apart their light can never reach us. Stars burn through their fuel, black holes evaporate via Hawking radiation, and space becomes a vast, frigid void where temperatures approach absolute zero. It's like a candle flickering out in an ever-growing room, leaving only embers too cold to reignite. Current observations support this as the most likely fate, with dark energy's relentless push showing no signs of slowing. But what if dark energy weakens over time? That's where the big crunch comes in. Gravity could regain dominance, pulling galaxies back together in a reverse of the Big Bang. Space would contract, temperatures soar, and eventually every atom in the universe collapses into a single point, a singularity mirroring how it all began. Some cyclic universe models suggest this could trigger a new Big Bang, restarting the cycle. The catch: for this to happen, dark energy would need to behave more like a fading force field than a constant, something today's data doesn't yet support. Then there's the Big Rip, a far more violent finale. If dark energy strengthens over time, it could eventually overpower not just gravity but all binding forces, first shredding galaxies, then stars, then planets, and finally atoms themselves. Even spacetime would tear apart, ending reality in a single catastrophic instant. Imagine inflating a balloon until its surface cracks, except the balloon is existence itself. Some theories, like phantom energy models, allow for this nightmare scenario, though it remains speculative. Finally, the sneakiest doomsday, vacuum decay. Quantum field theory suggests our universe might be in a false vacuum, a stable-seeming state that's actually a precarious ledge. If a quantum fluctuation tips us into a true vacuum, a bubble of destruction could race through space-time at light speed, rewriting the laws of physics as it goes. One moment, everything's normal; the next, chemistry, light, even matter itself cease to function. The terrifying part, this could happen anytime, anywhere, with zero warning. Thankfully, it's statistically unlikely but not impossible. So which fate is truly ahead? Right now, the Big Freeze leads the pack, with dark energy's steady acceleration matching supernova and galaxy cluster observations. But mysteries remain. Does dark energy's strength change? Are there hidden dimensions or undiscovered physics that could flip the script? Every new telescope, from the James Webb to next-generation dark energy surveys, brings us closer to the answer. One thing's certain, the universe's finale won't be boring. Whether it's a whisper, a crunch, or a rip, the end will be as spectacular as the beginning. The night sky is filled with hundreds of billions of galaxies, each containing billions of stars. Statistically speaking, the universe should be teeming with life. So where is everyone? This is the Fermi paradox, the glaring contradiction between the high probability of extraterrestrial civilizations and our utter lack of evidence for them. Enrico Fermi posed this question over half a century ago during a casual lunch conversation, and it still haunts scientists today. One explanation is the rare Earth hypothesis, the idea that while planets might be common, the precise conditions that allowed life to thrive on Earth are extraordinarily fragile. Think of our planet as a cosmic jackpot, not too close to the sun to boil away our oceans, not too far to freeze them solid. A massive moon stabilizes our tilt, preventing wild climate swings. Jupiter's gravity acts as a cosmic vacuum cleaner, diverting asteroids that could sterilize the surface. Plate tectonics recycle nutrients, and a magnetic shield deflects deadly solar radiation. Remove just one of these factors, and complex life might never have gotten a foothold. But what if life isn't bound to planets at all? Panspermia, the theory that life's building blocks can hitch rides on comets or meteorites, suggests that microbial life could be scattered across the galaxy like cosmic dandelion seeds. Some extremophiles, microbes that thrive in Earth's harshest environments, could theoretically survive the vacuum of space, raising the possibility that life didn't start here but was delivered from elsewhere. Imagine finding out we're all descendants of interstellar stowaways. Then there's the Great Filter, a hypothetical barrier that prevents life from advancing to interstellar civilization. It could lie in our past, meaning the jump from simple chemistry to complex life is so improbable that we're among the universe's first. Or worse, it could be ahead of us, some inevitable catastrophe, nuclear war, AI rebellion, ecological collapse, that dooms all advanced civilizations before they can spread beyond their home worlds. Meanwhile, the search for alien intelligence continues. SETI scans the skies for radio signals, while projects like Breakthrough analyze petabytes of data for artificial patterns. The discovery of exoplanets in habitable zones fuels hope. TRAPPIST-1, 7 Earth-sized worlds, or Proxima Centauri b, just 4 light-years away, yet so far silent. Perhaps the answer lies in scale. The universe is 13.8 billion years old, plenty of time for civilizations to rise and fall without overlapping. We might be like ants in a vast, deserted cathedral, unaware of the giants who walked here eons ago. Or maybe we're the first, destined to someday fill the void ourselves. Either way, the question isn't just academic. Finding we're alone would make life infinitely precious. Finding we're not, well, that would change everything. At the heart of nearly every galaxy, including our own Milky Way, lurks a supermassive black hole, not just a destroyer of stars, but a sculptor of galactic destiny. Far from being passive cosmic vacuum cleaners, these gravitational behemoths engage in a dynamic feedback loop with their host galaxies, shaping everything from star formation rates to the galaxy's ultimate size and structure. Take quasars, the universe's most luminous objects. These are supermassive black holes in their youth, feasting on vast amounts of gas and dust. As material spirals into the black hole's accretion disk, friction heats it to millions of degrees, blasting out enough radiation to outshine entire galaxies. But here's the twist: that energy doesn't just vanish into the void. It punches back into the surrounding galaxy with enough force to blow away star-forming gas, effectively putting a cap on how big the galaxy can grow. It's like a cosmic thermostat. When star formation runs too hot, the quasar switches on, cooling things down. Observations of distant galaxies show this process in action. The brightest quasars often reside in galaxies where star formation has mysteriously stalled. Then there are the relativistic jets, twin beams of charged particles shooting out at nearly light speed from the black hole's poles. These jets can stretch for millions of light years, carving bubbles in the intergalactic medium and heating surrounding gas so intensely it can't collapse into new stars. In some cases, like the galaxy M87, these jets are so powerful they've become visible across cosmic distances, a testament to the black hole's far-reaching influence. Yet paradoxically, these same jets can also trigger star formation when they collide with dense gas clouds, compressing them just enough to ignite new stellar nurseries. It's a delicate balance: too much energy and the galaxy is sterilized just enough and it's revitalized. This feedback loop explains a puzzling pattern astronomers have noticed. The mass of a galaxy's central black hole is eerily proportional to the mass of its surrounding bulge of stars. They grow in lockstep, as if connected by an invisible thread. Simulations now show why black holes and their galaxies evolve together, each regulating the other. When a black hole feeds, it grows more powerful, but its outbursts eventually starve it of new material, forcing it into dormancy. During quiet periods, gas accumulates again, stars form, and the cycle repeats. This cosmic symbiosis suggests black holes aren't just inhabitants of galaxies, they're architects, shaping their homes from the inside out. The implications are staggering. Without these feedback mechanisms, galaxies might burn through their gas too quickly, leaving the universe devoid of the long-lived stars necessary for planets and life. It's a reminder that even the most destructive forces in the cosmos can be creative, weaving order from chaos on scales we're only beginning to comprehend. Dark matter is the universe's most elusive ghost, an invisible force shaping galaxies and bending light, yet refusing to reveal itself. We know it's there because of its gravitational grip on stars and gas, but after decades of searching, we still don't know what it actually is. The leading suspect, WIMP, weakly interacting massive particles. These hypothetical particles are heavy, slow-moving, and barely interact with normal matter, making them nearly impossible to detect. Picture trying to catch smoke with your hands. That's the challenge physicists face when hunting for WIMP in underground labs like the LUX Zeppelin experiment, where ultra-sensitive detectors wait for the faintest flicker of a collision between a WIMP and an atom. So far, silence, but WIMP aren't the only candidates. Actions, another theoretical particle, are the featherweights of the dark matter world, extremely light but potentially swarming the universe in vast numbers. Unlike WIMP, actions wouldn't just ignore normal matter, they'd occasionally transform into photons in the presence of strong magnetic fields. Experiments like ADMX are tuning their detectors like cosmic radios, hoping to catch the faint whisper of an action converting into a wave of light. The twist: if actions exist, they might have been born from the same primordial symmetry breaking that gave rise to the strong nuclear force tying dark matter to one of the universe's fundamental puzzles. Then there's the wild card: primordial black holes. These aren't the black holes formed from collapsing stars, but ones that could have popped into existence in the universe's first chaotic seconds, when dense pockets of matter collapsed under their own weight. Ranging in size from an atom to a mountain, these ancient relics could be lurking unseen, their gravity the only clue to their presence. The idea got a boost when gravitational wave observatories detected mergers of black holes with unexpected masses. Could some of these be primordial? The catch is, if they're too small, they'd have evaporated by now via Hawking radiation, leaving behind nothing but a faint burst of energy. Not everyone's convinced dark matter is a particle at all. Modified Newtonian dynamics suggests gravity might behave differently at cosmic scales, eliminating the need for invisible matter. Instead of invoking dark matter to explain why stars at the edges of galaxies orbit faster than expected, Mann tweaks the math of gravity itself. It's like discovering your car's speedometer is off and fixing the gauge instead of assuming an unseen force is pushing you. Some galaxy rotation curves fit Mann predictions startlingly well, but the theory struggles to explain other observations like the bullet cluster, where gravity clearly bends light in places with no visible matter, a smoking gun for dark matter's existence. The truth is, we're grasping in the dark literally. Every experiment that comes up empty-handed forces us to rethink what dark matter could be. Is it a single particle or a mix of different entities? Could it interact with itself in hidden ways, forming dark atoms or even dark stars? The longer the mystery persists, the more creative the theories become. One thing's certain, solving this puzzle wouldn't just tell us what's hiding in the shadows. It would rewrite our understanding of the universe's most basic rules. What if everything we experience, every star, every galaxy, even the space between them, is just a projection, like a cosmic IMAX screen? That's the radical idea behind the holographic principle. A theory suggesting our three-dimensional universe might actually be encoded on a two-dimensional surface at its outer edge. Think of it like watching a movie. The images feel deep and lifelike, but they're really just patterns of light on a flat screen. Could reality work the same way? The seed of this idea came from an unexpected place: black holes. In the 1970s, physicist Jacob Bekenstein discovered that the entropy, or information content, of a black hole isn't proportional to its volume, as you'd expect, but to its surface area. Stephen Hawking later confirmed this, showing black holes radiate energy and shrink over time, raising a paradox. What happens to all the information swallowed by the black hole? If it vanishes forever, it violates quantum mechanics' core rule that information can't be destroyed. The holographic principle offers a wild solution. Maybe the information isn't lost. Instead, it's smeared across the black hole's event horizon, like a cosmic hard drive storing data in pixels so fine we can't perceive them. This led to an even bolder hypothesis. If black holes encode their 3D interiors on 2D surfaces, could the entire universe do the same? Enter the AD/CFT correspondence, a groundbreaking idea from string theory. It proposes a perfect mathematical duality between a higher dimensional space, like our universe, and a lower dimensional boundary where physical laws take a completely different form. Picture a hologram on your credit card. The flat, shiny surface contains all the information needed to project a 3D image. Similarly, our universe's physics might live on a distant boundary we can't see, with everything inside just a shadow of that deeper reality. But how could this possibly work? Imagine the universe as a giant sphere. All the events happening inside, planets orbiting, stars exploding, could be described by equations operating on the sphere's surface. The surface wouldn't just contain a copy of reality. In a deep mathematical sense, it would be reality, with the 3D world we experience emerging from it. It's not that we're illusions, but that the true source code of the cosmos exists in a form we can't directly access. The implications are staggering. If the holographic principle is true, space itself might be pixelated at the tiniest scales, with a fundamental limit to how finely we can divide it, like a digital image breaking into visible squares if you zoom in far enough. This could even solve the long-standing conflict between quantum mechanics and gravity, unifying them in a framework where gravity isn't a force in 3D space, but a side effect of information processing on the 2D boundary. Yet for all its elegance, the theory faces challenges. Our universe doesn't perfectly match the idealized models where ad/CFT works. Real spacetime is expanding, not static. Some physicists argue this makes the holographic principle more mathematical metaphor than physical truth. Others are searching for evidence in the cosmic microwave background, hunting for anomalies that might betray the universe's pixelated nature. Whether the holographic principle holds or not, it's reshaped how we think about space, information, and the very nature of reality. It suggests the universe might be simpler and stranger than we ever imagined, with all its complexity boiling down to information written on the cosmic equivalent of a flickering screen. And that raises one last haunting question. If we're just projections, what's projecting us? Look at the night sky in any direction, and you'll see something strange. The universe looks almost exactly the same everywhere. Galaxies cluster in similar patterns. The cosmic microwave background glows with nearly identical temperatures, and even the distribution of matter seems eerily uniform across billions of light years. This shouldn't be possible without some cosmic fix. Regions of space so far apart that light hasn't had time to travel between them should look wildly different. Yet they don't. This is the horizon problem, one of the most baffling puzzles in cosmology until you introduce the universe's ultimate magic trick, inflation. Picture two people standing at opposite ends of a football field, each holding a cup of coffee at exactly the same temperature. If they've never interacted, never shared heat or information, how did their drinks end up so perfectly matched? Now scale that up to the size of the observable universe, where some regions are separated by distances so vast that not even light could have bridged the gap in 13.8 billion years. How did they synchronize? The steady-state model, popular in the mid-20th century, tried to sidestep this by proposing the universe had no beginning. It simply expanded while new matter continuously appeared to maintain density. Like a river flowing at a constant rate, it would look the same at all times and places. But this elegant idea collapsed when the cosmic microwave background was discovered, revealing the universe did have a hot, dense beginning, one that left behind a uniform afterglow inflation alone could explain. Here's how inflation solves the problem. In the universe's first trillionth of a second, space expanded faster than light itself, stretching a speck smaller than a proton to the size of a grapefruit almost instantly. Before inflation, every part of the cosmos was close enough to interact, reaching thermal equilibrium, like those cups of coffee starting off in the same pot. Then inflation kicked in, pushing regions apart so rapidly they lost contact, but not before sharing that perfect uniformity. It's as if someone hit pause on a song, stretched the tape, then hit play again. The melody stays the same, just spread over a wider distance. The alternative, without inflation, the universe would be a patchwork of extreme temperatures and densities, like a splatter painting with no rhyme or reason. Instead, inflation's exponential smoothing left us with a cosmos so finely balanced that the temperature variations in the cosmic microwave background differ by less than 1 part in 100,000. That's smoother than the surface of a billiard ball scaled to the size of Earth. Critics of inflation point out it's almost too powerful. It doesn't just solve the horizon problem, it erases any trace of what came before, like a cosmic reset button. Some theorists argue for alternatives, like variable speed of light theories where light traveled faster in the early universe, allowing distant regions to sync up. Others propose bouncing universe models where a previous cycle of collapse and rebound naturally homogenized conditions. but none match inflation's simplicity or predictive power, like its precise forecast of those tiny fluctuations in the microwave background. The real marvel is how such a brief, violent event could leave behind a universe so orderly. Inflation didn't just set the stage for galaxies, it wrote the script, ensuring every corner of the cosmos followed the same rules. And that's the strange beauty of the Horizon problem. It's not a flaw in the universe's design. It's proof of something far grander, a moment when reality itself rewrote the laws of physics to give us a cosmos we could actually understand. The observable universe stretches 46 billion light-years in every direction, but that's just the portion we can see. Beyond that horizon lies an expanse so vast it defies comprehension, regions of space so distant their light hasn't had time to reach us in the universe's 13.8 billion-year lifespan. Yet cosmic inflation suggests this visible bubble is just a speck in a far grander cosmic landscape, one that might extend indefinitely or even infinitely, with conditions so alien they'd rewrite the laws of physics as we know them. Here's why we're cut off. The universe has been expanding since the Big Bang, and the farther away something is, the faster it recedes from us. Beyond a certain point, space itself stretches faster than light can travel through it, creating an impenetrable barrier, not because light stops, but because the space between us and those distant regions grows faster than light can bridge the gap. It's like trying to row a boat across a river that's widening faster than you can paddle. Even if you row forever, you'll never reach the other shore. But here's where it gets wild. Inflation theory implies this process didn't just happen once. It's ongoing in distant regions of space where new bubble universes might continuously form, each with its own unique physics. Picture a pot of water boiling endlessly with bubbles rising and popping, except each bubble is an entire universe, forever isolated from the others. Some of these bubbles could have stronger gravity, others might have extra dimensions, and a few could harbor forces we've never imagined. In some, the constants that dictate reality, the speed of light, the strength of electromagnetism, might be tweaked just enough to make matter unstable or chemistry impossible. This isn't pure speculation. The multiverse hypothesis, born from string theory and inflationary cosmology, suggests these alternate physics aren't just possible, they're inevitable. If the fundamental constants of nature are determined by random quantum fluctuations during inflation, then statistically, an infinite cosmos would produce every possible configuration somewhere. We just happen to live in a bubble where the numbers allow galaxies, stars, and life to exist, a concept known as the anthropic principle. Could we ever detect these other regions? Probably not directly. The space between us and them isn't just empty, it's expanding so violently that no signal, no force, no shred of information could ever cross the divide. But there's a tantalizing possibility. If another bubble universe collided with ours in the distant past, the shockwave might have left scars in the cosmic microwave background, subtle temperature variations or strange polarization patterns. Researchers have scanned the sky for these anomalies, and while none have been confirmed, the search continues. The real mind bender: if the universe is infinite, then somewhere out there, every possible variation of reality exists. An Earth where dinosaurs never went extinct, a galaxy made entirely of dark matter, even a version of you reading these words in a universe where gravity pushes instead of pulls. It's a humbling thought that our entire observable cosmos, with its billions of galaxies, might be less than a single grain of sand on an endless beach. And that beach, it might just be one of many. At the smallest scales of the universe, particles exist in ghostly superposition, being in multiple states at once until observed, while gravity warps spacetime into smooth curves on cosmic scales. These two pillars of modern physics, quantum mechanics and general relativity, work flawlessly in their respective domains, but bring them together and reality itself seems to fracture. The clash isn't just technical, it's a fundamental divide in how we understand existence. Take a black hole's singularity. Quantum mechanics says information can never be destroyed, yet relativity predicts the singularity shreds everything that falls in beyond recovery. Or consider the vacuum of space. Quantum theory sees it as a frothing sea of virtual particles popping in and out of existence, while relativity treats it as an empty stage where matter and energy perform. Merge these descriptions and the math explodes into infinities, a sure sign something's deeply wrong. It's like trying to combine a recipe for soufflé with instructions for building a bridge. The ingredients don't just fail to mix, they obliterate each other. String theory emerged as one ambitious fix, replacing point-like particles with tiny vibrating strings. These threads oscillate at different frequencies, producing all known forces and particles, a cosmic symphony where gravity and quantum effects harmonize in higher dimensions. Imagine plucking a guitar string to play every note in existence, from electrons to photons. But there's a catch. String theory requires at least 10 dimensions, 6 of which are curled up impossibly small. Worse, it predicts a landscape of possible universes, some with our physics, most without making concrete predictions nearly impossible to test. Loop quantum gravity takes a radically different approach. Instead of strings, it proposes space-time itself is woven from discrete, interwoven loops, a fabric of finite threads. Picture a pixelated universe where not just matter but time and space come in indivisible chunks. This elegantly avoids singularities. Black holes become ultra-dense knots where spacetime rebounds rather than collapsing. Yet, like string theory, it struggles to bridge the gap to experimental verification. The energy scales needed to probe these loops are beyond any particle collider we could build. Meanwhile, lesser-known contenders like causal dynamical triangulations simulate spacetime as tiny geometric shapes that spontaneously assemble into the cosmos we know, like Lego bricks forming a smooth curve when viewed from afar. Others explore emergent gravity, where spacetime isn't fundamental but arises from deeper quantum interactions, like temperature emerging from atomic motion. Why does this rift matter? Because until we reconcile these frameworks, key moments in cosmic history, the Big Bang's first instant, black hole interiors remain incomprehensible. The solution might require rewriting physics from the ground up, abandoning cherished assumptions about time, causality, or locality. Or perhaps, as with relativity and Newtonian physics, a deeper truth awaits, one where today's contradictions seem obvious in hindsight. Until then, the divide isn't just a gap in our knowledge, it's a frontier challenging us to rethink reality itself. We've been taught since childhood that our world has 3 dimensions: length, width, and height, with time as the 4th. But what if reality has hidden layers we can't perceive, dimensions folded so tightly they're invisible to our senses? This isn't science fiction. It's a cornerstone of string theory, which proposes the universe might have up to 11 dimensions to make its equations work. Imagine an ant walking along a telephone wire. From far away, the wire looks one-dimensional, just a line. But up close, the ant can move around the wire's circumference too, revealing a second dimension curled up at microscopic scales. This is how string theory envisions extra dimensions. They're compactified, coiled into spaces so tiny, about a billionth of a trillionth the size of an atom, that even our most powerful microscopes can't detect them. These hidden dimensions aren't empty either. They vibrate with the strings that make up all particles, like the intricate harmonics of a multi-dimensional violin. But there's another wild possibility: brain worlds. In this scenario, our entire universe could be a 3-dimensional brain, floating in higher dimensional space, like a slice of bread in a cosmic loaf. Gravity, unlike other forces, might leak into these extra dimensions, explaining why it's so weak compared to electromagnetism. Picture a watercolor painting where gravity's ink bleeds through the paper while other forces stay neatly on the surface. This could solve long-standing puzzles, like why the vacuum energy calculated by quantum field theory is so much larger than the cosmological constant we observe. How do we test these ideas? Particle colliders like the Large Hadron Collider hunt for signs of extra dimensions by looking for missing energy momentum that seems to vanish into unseen dimensions during high-energy collisions. Think of it like rolling a marble across a table and watching it mysteriously slow down, as if some energy leaked into an invisible dimension. So far, no luck, but physicists are pushing for even higher energy colliders that might finally spot these elusive effects. Gravity experiments offer another path. If extra dimensions exist, Newton's law of gravity should break down at microscopic distances, where the hidden dimension's influence grows stronger. Imagine gravity as a force that spreads thinly in 3 dimensions but becomes more concentrated if it has more directions to flow into. Ultra-sensitive torsion balance experiments, devices that measure gravitational attraction between tiny masses, have probed scales down to a fraction of a millimeter, searching for deviations that might betray a 5th or 6th dimension. The implications are staggering. If extra dimensions exist, they could unify all fundamental forces under one elegant framework, revealing that gravity's apparent weakness is just an illusion caused by most of its strength leaking into unseen directions. They might even explain the universe's accelerating expansion, with dark energy arising from interactions between brains in higher dimensional space. Yet skepticism remains. Critics argue that without direct evidence, extra dimensions risk becoming a theory of everything and nothing, able to explain any observation but predict none. Others point out that even if dimensions exist, they may forever remain beyond our observational reach, like shadows cast by a reality we can never fully grasp. Whether hidden dimensions are real or just mathematical mirages, their exploration pushes us to rethink the very fabric of existence. After all, if we've been wrong about something as basic as how many directions reality has, what else might we have missed? The answer could be lurking just beyond the edges of our perception, in dimensions we're only beginning to imagine. The cosmic microwave background isn't just ancient light, it's the universe's first baby picture, captured when it was a mere 380,000 years old. To understand why this faint glow is so revolutionary, rewind to that pivotal moment. The early universe was a plasma inferno, so hot that electrons zipped freely, scattering light like fog, obscuring a lighthouse beam. But as space expanded and cooled, electrons finally slowed enough to be snatched by protons, forming the first stable atoms. Suddenly, light could travel unimpeded for the first time, a flashbulb moment frozen in time and stretched by the universe's expansion into microwave wavelengths we detect today as a whisper from the dawn of time. What makes this glow so special isn't just its age, it's the imperfections. The CMB appears almost perfectly uniform, but subtle temperature variations, anisotropies, reveal a tapestry of slightly denser and sparser regions. These fluctuations are minuscule, differing by just 1 part in 100,000, but they're cosmic gold. Think of them as the universe's genetic code, tiny seeds that gravity would later nurture into galaxies and voids. Without these faint wrinkles, matter would have remained evenly distributed, and the cosmos would be a featureless soup forever. How do we know these anisotropies matter? Detailed maps from missions like Planck and WMAP show their patterns match predictions from quantum fluctuations stretched by inflation like fingerprints left by the universe's violent birth. Denser regions appear slightly warmer in the CMB because photons climbing out of these gravitational wells lost a bit of energy, like hikers struggling uphill. Conversely, sparser zones look cooler, their photons arriving slightly less depleted. This cosmic ledger of hot and cold spots became the blueprint for everything. Where you see a faint warm patch in the CMB, there's likely a supercluster today. A cold spot might trace a vast cosmic desert. But the CMB's secrets go deeper. Its polarization, the orientation of light waves, carries echoes of inflation's primordial gravitational waves, ripples in spacetime from the universe's first trillionth of a second. Some patterns, called B-modes, could reveal whether inflation truly happened or if something even stranger birthed the cosmos. Then there's that axis of evil, an unexpected alignment of large-scale anisotropies that some theorists argue might hint at pre-Big Bang physics or exotic topologies, like the universe being shaped like a gigantic donut. The CMB isn't just a relic, it's a time machine. By decoding its subtle patterns, we're reading the universe's origin story written in light and heat, a narrative that began before stars or galaxies existed. And with next-generation telescopes refining our maps further, who knows what other secrets this ancient glow might surrender? Could time travel be woven into the fabric of the universe itself? Einstein's theory of general relativity doesn't just allow for the possibility, it provides the blueprints. Take closed time-like curves, hypothetical paths through spacetime that loop back on themselves. Picture a cosmic racetrack where, if you could move fast enough, you'd return to your starting point not just in space but in time. The math checks out under extreme conditions like near a spinning black hole. Space-time could twist so severely that the future connects to the past like a Möbius strip. Physicist Kurt Gödel stunned the world with his solution to Einstein's equations, a rotating universe where every point acts as a time machine, dragging space-time along with it like syrup swirling in a glass. Wormholes, Einstein-Rosen bridges offer another tantalizing route. These cosmic shortcuts, linking distant points in space-time, could theoretically be adapted for time travel by placing one mouth near a black hole and the other in a slower gravitational field. Time dilation means clocks tick at different rates at each end, turning the wormhole into a tunnel not just through space but through ages. Want to visit the year 3000? Just step through, but here's the catch. Wormholes likely require exotic matter with negative energy to stay open, a substance we've never observed. It's like building a bridge where the scaffolding defies gravity, possible on paper, but physically improbable. Then there's the grandfather paradox, the ultimate wrench in the gears. If you traveled back and prevented your own birth, how could you exist to make the trip in the first place? Quantum mechanics offers a bizarre fix, the self-consistent universe hypothesis, where any action you take in the past was always part of history. Try to erase your grandfather and fate intervenes, your gun jams or you miss the shot. Alternatively, the multiverse theory suggests branching timelines where your actions spawn a new reality, leaving the original untouched. Theoretical limits abound. Hawking's chronology protection conjecture posits that quantum effects would sabotage time travel before paradoxes arise, like cosmic censorship guarding causality. Even if possible, the energy costs might be astronomical, or the journey might shred anything attempting it. Yet the fact that these ideas emerge from reputable physics, not fiction, hints at something profound. Time, like space, may be more malleable than we ever dreamed. So is time travel cosmologically possible? The universe seems to whisper yes, even as it guards its secrets fiercely. Until we uncover deeper laws or stumble upon a rotating universe, it remains the ultimate thought experiment, teasing us with glimpses of a reality where time is just another dimension to explore. Neutrinos are the universe's ghostly wanderers, particles so elusive they pass through entire planets like they're not even there. Born in the hearts of stars, the core of nuclear reactors, and the violent death throes of supernova, these nearly massless particles outnumber atoms in the cosmos by 1 billion to 1. Yet despite their abundance, neutrinos play hard to get, rarely interacting with ordinary matter. So how could something so faint shape the fate of the universe? The answer lies in their ability to tip cosmic scales in ways we're only beginning to understand. Take nucleosynthesis, the process that forged the universe's first atomic nuclei. In the Big Bang's fiery aftermath, protons and neutrons struggled to form stable pairs until the cosmos cooled enough for them to stick. Neutrinos acted as subtle referees in this particle dance. Their weak interactions with matter influenced the delicate balance between protons and neutrons, ultimately determining how much hydrogen, helium, and lithium the early universe produced. Even a slight change in neutrino behavior could have left the cosmos with far less helium, altering the chemistry of every star that followed. It's impressive for a particle that barely seems to exist at all. Their role in supernova is even more dramatic. When a massive star collapses, 99% of its energy doesn't explode outward as light. It's carried away by neutrinos in a pulse so powerful it can outshine the entire galaxy for seconds. This neutrino shockwave is what propels the star's outer layers into space, seeding the universe with heavy elements like iron, gold, and uranium. The iron in your blood, the gold in your jewelry, all of it was forged in these catastrophic blasts and scattered by neutrinos. Without them, supernova might fizzle instead of explode, leaving the cosmos bereft of the raw materials for planets and life. But neutrinos might hold an even bigger secret. They could be part of dark matter. We've long assumed neutrinos are too light to account for the universe's missing mass, but what if we're wrong? Enter sterile neutrinos, a hypothetical heavyweight cousin of the three known neutrino types. These particles wouldn't interact via the weak force at all, making them utterly invisible except through gravity. If they exist, sterile neutrinos could be the glue binding galaxy clusters together, their sheer numbers compensating for their tiny individual masses. Some theories even suggest these mysterious particles might decay, producing faint X-ray signatures astronomers are now hunting in distant galaxy clusters. The challenge is catching them. Neutrinos are famous for slipping through detectors like phantom thieves. Trillions pass through your body every second without a trace. Yet ingenious experiments like IceCube, a telescope buried deep in Antarctic ice, and Super Kamiok, and a tank of ultra-pure water in Japan, have turned the planet itself into a neutrino trap. When the rare interaction occurs, it creates a flash of light or a trail of bubbles, offering clues to the particle's origin and energy. Recent detections of high-energy neutrinos from Blazar's distant galaxies with supermassive black holes prove these particles can traverse billions of light-years, carrying information from the universe's most violent events. What makes neutrinos so fascinating isn't just their stealth, it's how they force us to rethink the rules. They oscillate between types mid-flight, defying early assumptions that they were massless. They violate symmetry in ways that might explain why the universe favors matter over antimatter. And their sheer abundance means that even if each one exerts only the faintest influence collectively, they sculpt the cosmos in ways we're only starting to measure. Their story is a reminder that the universe's most powerful actors aren't always the loudest. Sometimes they're the whispers in the dark. The particles that slip through walls carry the echoes of dying stars and might just hold the key to the universe's invisible skeleton. And as we learn to listen, we're finding that these spectral travelers have been shaping reality all along. Magnetic fields are everywhere in the universe, wrapped around galaxies, woven through interstellar clouds, even threading the voids between clusters. But here's the cosmic puzzle. How did they get there? Unlike fridge magnets with obvious sources, cosmic fields are invisible forces that somehow grew from nothing to shape the evolution of the cosmos. The story begins in the universe's infancy, when the tiniest quantum fluctuations might have planted the seeds for magnetism on a galactic scale. Imagine the early universe as a supercharged plasma, a roiling sea of particles too hot to form atoms. In this chaos, even the slightest unevenness, perhaps leftover ripples from inflation, could have created weak magnetic fields. Picture stirring a cup of coffee and watching tiny whirlpools form. Similar motions in the primordial plasma could have stretched and twisted these initial threads, amplifying them through dynamo effects. But here's where it gets wild. These fields weren't just passive bystanders. They became cosmic puppeteers, guiding how gas collapsed into galaxies and stars. Without them, the universe might look radically different, like a city with no roads to channel traffic. Fast forward a few billion years and plasma dynamics took over. When galaxies formed, their rotating disks of ionized gas acted like colossal generators, spinning charged particles and turning kinetic energy into magnetic energy. It's the same principle as a bicycle dynamo, where motion creates a current but scaled up to galactic proportions. Supernova added fuel to the fire. Their shockwaves rattled through interstellar space, compressing and strengthening these fields like blacksmiths hammering molten metal. Over time, what began as faint whispers grew into vast, organized structures, some stretching hundreds of thousands of light years along spiral arms. But magnetic fields don't just shape galaxies, they're interstellar accelerators. Cosmic rays, those high-energy particles racing through space at nearly light speed, owe their existence to these invisible force grids. Fields act like cosmic pinball machines, bouncing particles back and forth until they reach unimaginable energies. Some of the most powerful events in the universe's active galactic nuclei, gamma-ray bursts, might rely on magnetic fields to focus their explosive power into jets sharper than any laser. Yet mysteries remain. Why do some galaxies have fields 1,000,000 times stronger than others? Could primordial magnetism explain the universe's large-scale structure? And what about the voids, those vast, empty regions between galaxy filaments? Even there, faint magnetic fields might lurk, remnants of a time when the universe was young and everything was connected. The search for answers is pushing telescopes and simulations to their limits. Experiments like CMB-S4 are hunting for imprints of primordial magnetism in the cosmic microwave background, while radio astronomers map galactic fields by studying how they twist the light from distant quasars. Every new observation peels back another layer, revealing how something as intangible as a magnetic field could quietly sculpt the universe, one charged particle at a time. The universe is almost completely empty, a cosmic void where matter is the exception, not the rule. If you took all the atoms in the observable universe and squished them together, they'd fill less than 1/1000th of its volume. So how did a reality born in fire and density become so astonishingly sparse? The answer lies in the delicate balance between expansion, atomic structure, and the eerie energy lurking in what we call empty space. Rewind to the universe's first moments, when it was a seething, ultra-dense plasma, so packed that particles couldn't move without constantly colliding. But as space expanded, matter thinned out, pulled apart by the relentless stretching of spacetime itself. Here's the catch: while atoms formed when electrons settled into orbit around nuclei, they're mostly hollow. Imagine a hydrogen atom scaled up to the size of a football stadium. The nucleus would be a single grain of sand at midfield, and the electron a speck buzzing somewhere in the stands. The rest pure emptiness. This vast nothingness isn't a flaw, it's a necessity. If electrons snugged closer to nuclei, quantum mechanics would collapse atomic orbits, making chemistry as we know it impossible. No molecules, no water, no life, but emptiness isn't passive. Even in the deepest vacuum, quantum fields hum with activity, particles flickering in and out of existence so fast we can't detect them directly. This vacuum energy exerts a sort of negative pressure, ironically, the same force driving galaxies apart today. In the early universe, matter's gravity fought this expansion, but as space grew, matter diluted and dark energy took over. Now the cosmos doesn't just contain emptiness, it's dominated by it, with vacuum energy dictating the pace of cosmic evolution. The real twist: this emptiness is why we exist. If the universe were even slightly denser, gravity would have pulled everything back into a big crunch eons ago. Too sparse, and matter would have scattered too wildly for galaxies to ever form. Our Goldilocks emptiness, balanced between quantum rules and cosmic expansion, created the perfect conditions for structure to emerge. So next time you gaze at the night sky, remember, the void isn't just empty space. It's the stage that made all the rest possible. Two particles separated by billions of light years instantly mirror each other's quantum states, no signal passing between them, no hidden wires. This spooky action at a distance, as Einstein called it, defies everything we know about locality and causality. Yet quantum entanglement isn't just real, it's the backbone of emerging technologies like quantum computing. What if this bizarre phenomenon isn't confined to lab experiments? What if it's woven into the fabric of space-time itself, shaping the universe on cosmic scales? Enter the ER=EPR conjecture, a radical idea that bridges quantum mechanics and general relativity. Named after two landmark physics papers, Einstein-Rosen-Err on wormholes and Einstein-Podolsky-Rosen-Epper on entanglement. This proposal suggests that entangled particles might be connected by microscopic wormholes or Einstein-Rosen bridges. Picture two black holes linked through their singularities, forming a tunnel through space-time. Now shrink that tunnel to the quantum scale, and you've got a possible explanation for entanglement. Particles aren't communicating faster than light. They're literally tethered by a hidden geometric thread. It's as if the universe stitched its seams with invisible quantum threads, tying distant points together in ways that defy classical intuition. This isn't just theoretical poetry. If ER=EPR holds, it could solve black hole information paradoxes by treating entanglement as spacetime's underlying structure. When particles fall into a black hole, their information might not vanish. It could be encoded in Hawking radiation via entanglement, preserved through these ghostly wormhole connections. The firewall controversy, where quantum mechanics and relativity clash at the event horizon, might dissolve if entanglement and wormholes are two sides of the same coin. Imagine the black hole's interior as a quantum hologram, with every bit of information mirrored on its surface through entangled links, like a cosmic zip file decompressed into reality. But the implications stretch further. Some theorists speculate that entanglement could explain the universe's large-scale uniformity, the horizon problem. If distant regions of space were once quantum entangled during inflation, their synchronized properties might persist even as they're pushed apart by expansion. It's like tearing a photograph in half and finding both pieces still perfectly aligned, not because they're communicating, but because they were never truly separate to begin with. Critics counter that ER=EPR remains untested, a tantalizing mirage in the desert of quantum gravity theories, yet experiments are inching closer to probing these ideas. Quantum simulators attempt to recreate wormhole dynamics in controlled settings, while gravitational wave detectors hunt for echoes of microscopic spacetime tunnels. Even if the conjecture falls short, it's reshaped how we view entanglement, not as a quirk of particles, but as a fundamental feature of reality's architecture. The most thrilling possibility, if spacetime itself emerges from a quantum network of entangled connections, like a 3D projection of deeper, entangled data. We might be living inside a cosmic hologram where every here is secretly linked to every there, and the universe's deepest secrets are written in spooky, silent threads we're just beginning to trace. What if consciousness isn't just a byproduct of the universe? What if it's the other way around? This radical idea, lurking at the edges of physics and philosophy, suggests that the mind might play a fundamental role in shaping reality itself. At first glance, it sounds like science fiction, but some serious thinkers argue there's more to the connection between observer and cosmos than we've dared to admit. Consider panpsychism, the view that consciousness is a universal feature of existence, as intrinsic to matter as mass or charge. In this framework, even subatomic particles might possess a rudimentary form of experience, not thoughts or feelings, but a raw proto-consciousness. Think of it like this: an electron doesn't think, but it might have some infinitesimal inner aspect, a whisper of subjectivity. When billions of these particles combine in systems as complex as brains, fuller consciousness emerges, like countless droplets merging into an ocean. It's a dramatic departure from the conventional view that consciousness arises solely from neural complexity, implying instead that it's been here all along, woven into the fabric of reality at the smallest scales. Then there's the participatory universe hypothesis, inspired by quantum mechanics' observer effect. In experiments like the double slit, particles behave differently when measured, as if aware they're being watched. Some interpretations, like von Neumann-Wigner, take this further, proposing that consciousness collapses quantum probabilities into definite outcomes. Without an observer, reality remains a blur of possibilities. Imagine a tree falling in a forest with no one around. In this view, it doesn't make a sound or even fully exist until consciousness interacts with it. Mainstream physics balks at these ideas, and for good reason. They're notoriously hard to test, drifting into metaphysics. Yet the hard problem of consciousness, why subjective experience exists at all, remains unsolved by conventional neuroscience. Maybe the universe's deepest mystery isn't dark matter or quantum gravity, but the very nature of awareness. Could answering one solve the other? The jury's out, but the question lingers, haunting the boundary between science and wonder. From the unimaginable spark of the Big Bang to the eerie silence of the Fermi paradox, these 30 questions don't just challenge what we know, they reveal how much we have yet to discover. Each mystery peels back another layer of the cosmos, leaving us humbled and awestruck. How did quantum fluctuations sculpt galaxies? Why does dark energy push the universe apart while dark matter holds it together? Could black holes be portals to other realities? The more answers we find, the more breathtaking the questions become. This journey through cosmic enigmas isn't just about science, it's a reminder that curiosity is humanity's superpower. Every time we point a telescope at the night sky or smash particles in a collider, we're not just seeking data, we're chasing wonder, trying to grasp our place in a story far grander than we can fully imagine. Maybe that's the real magic of these questions. They don't just teach us about the universe, they teach us how to marvel at it. So which mystery lingers in your mind? The fine-tuning of physics that made life possible, the haunting possibility of parallel worlds, or the chilling thought that we might be alone in the void? Drop your favorite question in the comments. I'd love to hear which cosmic puzzle keeps you up at night. And if you're hungry for more mind-bending explorations, hit subscribe. The universe has endless secrets left to share, and together we'll keep uncovering them one question at a time. After all, the greatest discoveries begin with a single, thrilling thought. What